Hello, everybody, and welcome to my now remote talk on leveraging Ngram for quantum malware detection. My name is Jenn Ferreras. Actually, hold on. My name is Dr. Jenn, and I am currently a malware analyst and researcher, as well as a detections engineer. I was supposed to be there. I actually get a lot less nervous if I'm in person, but this is what happens. So before I start, I think it's very, very important that I let you guys know that I am nowhere near being super knowledgeable when it comes to quantum computing. And if you are one of those humans who grasp all of the quantum concepts, you are already miles cooler than me, and I would like to be your friend. So if you're one of those, please reach out to me because I'm here for it. All right. So malware, quantum computing, and Ngram all live in this world of pattern and complexity, this pattern recognition system, right? But what actually happens when they collide? That's basically what we're going to talk about in this presentation. The presentation will go something like this, where I'm going to introduce a very skinny, very bare bone malware evolution or malware detection evolution. We're going to talk about Ngrams, quantum integration, and the weird future that I kind of see coming along the way. Now, this very dirty look on how malware detection has evolved around like throughout time, right? We started with signature-based detections. These were super great for identifying known threats, but kind of completely entirely blind to anything new. It was like using a wanted poster. They're effective only if the criminal has already been caught once before. Then came the heuristic and behavioral detection, which looked at what a program does and not just its code. That made it a little smarter, more dependable, but still, attackers and even myself learned how to kind of mimic normal behavior and slip through, right? So today we are mostly relying on AI and machine learning, systems that can learn, adapt, predict, and do all the fun little things, right? So it sounds good, but this level of intelligence usually comes at a price. Imagine how much data requirements, computational cost, and at the end of the day, it's still not perfect. The truth is, malware evolves constantly, all the time, and if our defenses don't evolve faster, then we will always be playing this catch-up game. If you have no idea what Ngram is, you are not alone. I did not know until probably the beginning of this year. So let's talk a little bit about it. This is kind of the bread and butter of pattern matching. Ngram works by breaking malware down into short sequences of bytes or code. Think of it like splitting a sentence into small words or chunks, right? Once we have those pieces, we start looking for patterns, how often these sequences appear, where they show up, and how they repeat. That repetition becomes our clue for spotting not just familiar malware, but even variants that have been obfuscated or slightly altered to kind of hide the identity, right? It is simple, it's reliable, and it's a technique borrowed straight from natural language processing, if you are familiar with it. The same methods used to teach machine learning how to understand human language is used here in Ngram. But there's a catch. It's also very slow, and by itself is not necessarily enough to kind of outsmart modern malware. Still, it kind of lays a foundation for everything else, especially when we start mixing it up with quantum approaches later on. Now, for those people who are like me that are a little visual, like I said, this is kind of like an introduction. When you use Ngram in a learning mechanism, it breaks things like this. Let's say that the graphs are the two pieces that we want to identify. It kind of breaks the code, the malware, or the sentence into little pieces that can be identified on its own. It doesn't have to be an extensive code, but little pieces and bits that it's going to be like, okay, this is consistent between multiple different strain of malware. This might be something that we need to look into. All right, let's go back to the basics when it comes to quantum computing. All right. Like I said, this once again is the super basics. In the classical world, bits can only be 0 or 1. They're either one or the other. But when we're talking about qubits, it can be both at the same time. This is thanks to superposition. Think of it like multitasking on steroids, honestly. Or the example that you're going to find everywhere you read is imagine a coin just spinning nonstop, right? When we think about this, think about the possibilities. If you are yes and no all the time, if you're up and down all the time, if you are black and white all the time, it becomes very, very, very easy for you to have the right answer often, right? But now, quantum computer also has something called entanglement. This is kind of spooky. Is two qubits can influence each other instantly, no matter how far apart they are. Doesn't matter where they are in the system. I find this a little funny because Einstein literally called it spooky action at a distance. And then when it comes to quantum computer, we have what we know as speed. Because quantum systems can process countless possibilities in parallel all at once, they can tackle problems that would take classical computers centuries to solve. So we have a qubit that is 100% of the times is 1 and 0 all at once. We have entanglement, which basically says that all the qubits are influenced by one another instantly, no matter how far apart they are. And then we have speed. And I think the speed comes from being qubits and having entanglement. So when we compare qubits to bits, we're really, really talking about a massive leap in parallelism, basically working side by side, which makes this whole system, this whole idea incredibly powerful for things like big data analysis and, well, malware detection. But like I said, with great power comes a lot of weirdness and sometimes complexity. Quantum gives us incredible potential, but it also kind of rewrites the rules we thought we once understood. Once again, with the visuals, this is how I learned, so bear with me right here. Classical computer, you either have a 0 or a 1, either or, there's a state. When it comes to qubits in the quantum computer, then you have ones and zeros superimposed on one another, and they're simultaneously both. Now, here's the thing about quantum. It is powerful, yes, it sounds super cool, but it's also extremely finicky. Quantum systems are incredibly sensitive. The slightest vibration, a change in temperature, or even a stray electromagnetic wave can throw everything off. This even has a name. This is called decoherence. And it can destroy the quantum state in microseconds. Then we have the data conversion. If anybody here is a mathematician or a physicist, I actually studied math at some point in my life. You know, I'm a chemist. So unit conversion is something that is extremely important and very, very annoying. When it comes to data conversion, everything we use today, text, numbers, code, it's kind of in the classical language. Before we can even use it in quantum computers, it has to kind of be encoded into a quantum-friendly format. Imagine how time-consuming that would be. Jesus, and messy. Then we have accuracy. This is another huge issue that we encounter often. Despite all the hype, many quantum models are still less accurate than classical ones, especially when you add noise into this mix. Let's not forget error correction. Every logical qubit might require dozens or even hundreds of physical qubits to stabilize it. That's a huge limitation when it comes to scalability. Something that I failed to mention, uh, our classical computing are mathematical and quantum computer are physics. If you know anything about physics, it can get interesting very quickly. So, having said that, it is important for it to recognize, because it is a thing, that we are still in what's called the NISQ era, which is a noisy intermediate scale quantum state. We got brilliant theories. I have about 1,000 of them. Amazing algorithms, but the hardware is not really there just yet. Now, despite all of the finicky quantum behavior, there's one algorithm that really shows what's possible. Let's talk about Grover's algorithm. It is a quantum search algorithm that can find a specific item in an unsorted list of quadratic in an unsorted list, but it can do it quadratically faster than a classical brute force. Imagine having answers for that password crack on any CTF in seconds instead of minutes, right? In other words, what might take a classical computer hours, days, could take a quantum system just a couple of minutes. That is, as long as the temperature and the sound and vibration and everything is working in your favor and you have the blessing of the moon. So in 2026, 2022, all good. And Nicholas tested something absolutely brilliant. That is the one word that I have. I kind of analyzed multiple of the research and it was just great. They grabbed Grover's algorithm for finding things very quickly and on in an unsorted list or group of things, and they combined it with ngram to match malware hashes. And guess what? It actually worked. It actually worked. Even when they did this on quantum simulators, we're going to talk about simulators on the side. I have been crying myself to sleep about them. They actually achieved faster pattern matches and more efficient malware classification using this combination of Grover's algorithm and ngram. So think about this for a second. We have the capability of search a massive amount of data very quickly and then search it granularly in a granular way, and where you can find little tiny repeating patterns without having to account for the whole entire word or the hashes in their case. Um, if anybody here has ever done any type of detection engineering, I have. It can be cool and frustrating all at once. Imagine malware detection that doesn't just kind of react, but it predicts and adapts to in real time. Imagine having these changes that you don't have to fine tune or tune all your detections all the time, but they're kind of learning from each other and picking up on the things that it sees. That's I know that's a little far-fetched and it is kind of future potential, but real-time malware detection at a scale, I think is definitely achievable once this quantum hardware catches up to what we need. You know, it's not really science fiction. It's kind of like the beginning of a new cybersecurity rabbit hole that I'm probably going to fall into. Actually, I already fell into it. All right, so quantum simulators. Quantum simulators are a thing. I am a researcher and I actually have access to a quantum computer, but I have not grown a pair to go and actually use it because I am terrified that I'm going to break something. And I'm going to be that one person that touched it and broke it. So I wanted to find a different way to kind of start experimenting before I decide to actually walk in there. And this is where quantum simulators come into play. Now, let's be real. You know, most of this quantum malware magic isn't really happening on those computers, considering that people like me don't even want to touch them. So think of quantum simulators like quantum with training wheels. It doesn't translate like a normal classical computing will translate into a virtual machine. It doesn't do kind of the almost one-to-one ratio, but it is close enough that you can have and develop some theories and develop some hypotheses and kind of test them out as long as you have a lot of resources and a lot of patience. So real quantum hardware is rare. If you've tried to find one, there's very specific computers in different places. They're very expensive and honestly, surprisingly, they're very noisy. They're very loud. A server room has nothing on a quantum computer. Remember, just keep that in mind that we're still in that NISQ era, so we got to be a little patient. And also remember that we are still dealing with the decoherence and the instability of the constant issues that actual physical quantum computers bring. So instead, people like me, we try to use quantum simulator to test those super cool algorithms like the Grover or the quantum enhanced gram n-gram models in this kind of control environment. They're not perfect. They're not perfect by any means. Simulators don't actually replicate all of the messy real world errors that you get in a quantum machine, but they're essential for this kind of prototyping and refining and validating those ideas that come out of the blue to people like me or anybody wanting to experience with things that I don't really completely grasp just yet. So in short, these simulators are our bridge when it comes to uh, connecting what's possible today to those breakthroughs that we probably are going to be seeing tomorrow. I've already spoken about quantum machines, engram, and malware. So, what about this quantum malware, right? We don't have that yet. That is the short of it. We do not have quantum malware yet. Oh, as long as I know. If you guys do, then please share, but we don't have that yet. Now, let's play with a thought though. What if malware could actually run on quantum systems? Or worse, what if it could use quantum algorithms to hide itself, to mutate, actually mutate faster than we can even detect, or to crack encryption in seconds, right? For now, it is theoretical. It is a thought, a very exciting, equally exciting and scary one, but it is something that is definitely possible. As quantum hardware keeps evolving, that for now continues to shrink very fast. One thing that I was teaching recently was the fact that not even 100 years ago, because 100 sounds like a lot, many years, but computers started being a whole room of equipment with a printer, and you had to kind of read the paper to be able to see what was going on. I kind of visualize quantum computers that way. They're still big, bulky, with a lot of errors and a lot of interference and all of these issues, but their potential is so great that I'm pretty sure that we're going to be working towards improving this, making them more accessible, making them maybe cheaper, not as cheap, but maybe cheaper and more obtainable for maybe not me, but for other organizations that are going to have them readily available. The line between defensive innovation and offensive exploitation has always been thin. But what about quantum? Quantum might actually erase it entirely. If you have malware that it is constantly shifting, like instantly, and then you have detections that are also instantly shifting as fast as the malware is shifting, where is the line drawn, if one at all? Now, the real question here is, or isn't, if we can. I think the question is we should. And I agree. I think we should experiment with everything because I'm the type that likes to build things, to break them and build them again. That's how I learn. But once again, somebody somewhere at some point probably said just because we can doesn't mean that we should. But we probably will experiment with this malware life and this quantum experience. So chaos or clarity? Honestly, maybe a little bit of both. Quantum and engram together have this potential to kind of redefine malware detection or to confuse every single researcher in the room right now, trying to make them work. It's either or. That's like a very weird balance there. Right now, it is a fascinating mix of innovation and overcomplication. And that's kind of okay for me. Every big advance usually starts very complicated and ununderstood. We are, I believe, from my actual research, that we are at that point where we're making changes that are transformative. They're not perfect by any means. They're not ready for production, not even close, but they're kind of promising. So if any of you want to keep searching, researching with me, that would be great. Keep experimenting. Most importantly, keep being weird, because that's how we figure things out. In chaos, that's where clarity comes out from. And the next big break might be me next year telling you about my quantum computer that I probably broke and fixed. But that's not here nor there. Now, are there any questions thus far? I guess not.
We're gonna mic up someone for a question.
Sure.
The certificate authorities have been pushing fear mongering, the breaking of encryption, and they've been aligning it to, any month now. What do you think the timeline to getting quantum technology in more of a usable state in industry? Are you more of a? Do you think it's ever any month, any year, 10 years? What's your prediction for how soon we should be worried about this?
Well, honestly, I don't think we should be worried about this anywhere between now and 5 years from now, not even 10. The the primary issue when it comes to quantum computing, as I said, it is a a system that relies on physics. Physics is something that it is not finicky, it is actually very exact, but it does require a very specific environment. And as of right now, unless you're running a quantum machine in a nearly vacuum state, it is not going to be feasible to get anything in any type of consistency. Now, it is not only the fact that quantum machines are super expensive, huge, and kind of like, besides the fact that they have a big brain, kind of unusable, I think it's just that there's too much going on. And you got to understand that quantum computing, yes, everybody, well, not everybody, but a lot of different fields are trying to leverage this quantum computing brain power. However, not a lot of focus is being done in developing quantum computers that can be accessible to, I'm not even talking about the normal day-to-day analysts. I'm talking about big organizations. Right now, as we speak, there are enough, like, the number of quantum computers that are available in general are, you can count them with two hands. And in this continent, I'm not even talking about in the US, in this continent, right? So it is going to take a very long time for it to catch up. If we are going to be worried about breaking encryption, I wouldn't be worried about breaking encryption with quantum. I might be worried about other techniques that can be used for this purpose. Any other questions? Did I answer your question?
You answered his question.
Awesome.
I see no other questions in the room. Any questions on Discord? Nope. Okay. I think we're good. Thank you,
All right.
Jennifer.
Thank you very much for having me. Like I said, I wanted to be there. I wanted to see my peoples, but I wasn't able to. So I hope you guys enjoy my talk.